Okay. So at the end of the last meeting, we had sort of wrapped up the discussion of value function approximation techniques. And the way these techniques work is we're going to use some parameterized function and use a gradient update rule to try to get it to approximate the true value function of the particular policy that we're following. And this is inspired by all the tabular methods where we also learn a value function either exactly or by estimating it. And then we use the policy improvement theorem to solve the control problem, where we have some guarantees, at least in the tabular case, of improving the policy by following the greedy policy with respect to the value function. And this is where we take the argmax of the action value function, or we derive the action value function from the state value function if we have enough information about the environment. So in the approximation approach, we have this function that we're using with parameters where we're trying to approximate the true value function. And then we can still do the policy improvement by taking this argmax, but this is no longer guaranteed to work in the same way. But we're going to like the policy we're actually going to follow when we collect samples from the environment is going to be derived from, in this case, the approximated value function. And then in order to actually derive the gradient update rule, we have to define this objective function where in the most common case we first introduced, we're using the value error. And this is the difference between the true value function and our value function approximation. Yes, at weighted by the on policy distribution, right? So this is like how the states are distributed when we're actually following this policy function. So, what one of the here, so in chapter 10, this covers this control problem where we have this gradient update rule, right? With the weights, and like this is the gradient update rule for the state action value function. This U is some sample that we're using for the true value function. And when you do this with a Monte Carlo technique, this would just be an actual sample of the discounted return. This is showing a TD update rule where we're using a bootstrap approximation for U, where we're using a one-step reward and then our value estimate at the next state. And of course, this has its own set of problems. Oh, sorry, I guess Adobe wants to crash now, but this has its own set of problems because now our estimate actually depends on the parameters as well. And that's why these techniques are called semi-gradient control techniques.
So wait,
So
just to clarify, that first equation is for Monte Carlo, but the second is for Sarso, or?
U is generic. So the first equation is showing like generically we need something. If I go back to here, we need something to give us an estimate of this, where this is the true value function.
Okay.
So this can either be a sample of G, where like G in the parlance of this is the discounted return, or if we're in the average reward setting, it's the average like return we'd expect, the differential return from where we are at this time step. So
Okay.
when you do Monte Carlo, you have a true gradient method where you are actually collecting a sample of this, which is independent of the parameters themselves. But when we do a SARSA method, which is common because that way you can start doing updates immediately. You don't have to wait for an episode to terminate, which might not even happen depending on your problem. Then well, here, I have it written out here, but yeah. So with the semi-gradient methods, right, we're actually using our target this is called a bootstrap target because we're using the value function itself in the target. And this, if you go back and look at the notes where we covered this, this results in convergence to the TD fixed point, which is actually different from the true value function. Anyway, the point is there are there are several things that could go wrong with this value function approximation approach. Um, the main one being that the policy improvement step is no longer guaranteed to actually work. But then you have further complications with the TD fixed point. I mean, nevertheless, these methods can still work pretty well, and you just have to test it on a problem. But you should know that there's a lot of performance guarantees that go out the window that we previously had with the tabular methods.
If you could you
Okay.
explain the fixed point real quick? Or like I
Um,
understand TD, but I don't understand what fixed point is. Like if it's too much, so like we can skip over it.
it is I so yeah, it's a little involved. And if you go back, this is sort of covered in chapter 9, 10, and 11. It even gets further into it. I believe there's a figure here that shows it. Um, this is showing like a very simple um, random walk example. And the true value function is this green line here. See, and then this is showing different, either using a Monte Carlo estimate or TD learning. Again, this is similar to the control problem I saw. It's actually like the same kind of gradient update. It's just a different context. But when we do the TD value estimate, you can actually see that this is converging to a value function which has a higher error than the Monte Carlo estimate. And that's because this is a semi-gradient method, and you can actually prove it will converge to a different function. Now, hopefully, in most cases, that function isn't different enough from the true function that it ruins what you're trying to do. But it certainly could be. So, yeah, if you look at chapter 11, and there's a video, there's probably like one or two videos where we discuss it, but there's
Okay.
this like deadly triad problem where if you combine bootstrapping with TD learning and off policy sampling, you can end up with divergent behavior
Okay.
and all kinds of problems. But again, that's like a really bad scenario. But I'm saying like even without those problems, um, like even with true gradient Monte Carlo methods, like this is still not guaranteed to work because we are now using an approximate value function. And the main thing that these techniques rely on is the policy improvement theorem, which is only true in the tabular case, where all of the states can be neatly separated and they don't interact with each other. When we do approximation, as you can see in this diagram, this very simple approximation function you can see is clearly like grouping a bunch of states together that should have distinct values. And even though this is very simple, this is not like a complicated like neural network architecture. The principle is the same, that the actual function, like states are not independent. And when you change the parameters to change the prediction at one state, it will end up affecting other states. Either in this very simple case, it would just shift all of these states together. In a neural network, the states will be connected in a very, a very complicated way. But
Okay.
but the problem is that they're connected in the first place. So okay, so actually, so if we look at this now, update rule. So we need to compute this gradient, right? Like this is really the key step that we need. So like we have some function here. Like this function could be anything. It could be a linear function. It could be nonlinear. It could be any number of nonlinear architectures. But we have to be able to compute the gradient with respect to the parameters and a particular. In this case, this is for an action value function. So this would be the gradient of this function at a particular action value output, right? This is not the gradient of like the error function. This is just like the gradient with respect to the output of this function. So we have to compute this gradient, and then this is just showing it as this simple addition rule. Really, this is like an element-wise addition here, where this plus means that we're updating, right, all of these parameters with the gradient. This gradient will have the same shape as the parameter, like vector, or the parameter, whatever the data structure of the parameters is. Like once we compute this gradient, we're going to have something which looks exactly the same as the parameters. Like it'll match element by element, and then we have to do this element-wise addition to do the parameter update. So that's the main step we need for this. This is like the very simple pseudocode for semi-gradient Sarsa. You see, we have to compute the gradient update. We also need, when we're doing these sort of Sarsa algorithms, we need to also just compute the value function output, um, right? Which in the case of like a neural network, this would just be like a forward pass, whereas this would require both the forward and backwards pass. If we do this, we should, actually like save the forward pass so we don't have to redo it. Um, for this value, for example, like this has the same arguments as this gradient, but we will have to compute a separate forward pass for this look ahead step here. Okay. So then, and also, this is happening one step at a time, right? So when we compute this, like this function is operating on a single example where S is the state that we're evaluating. And this will have to be converted into a vector as well. We covered that last time, right, with the discussion of what's needed when we do approximation. We need this mapping of states to feature vectors, right? So the approximation function will operate on the feature vector associated with that state. And in the case of linear approximation, our parameters will just be a vector of equal length to the feature vector. But with nonlinear approximation, we're free to have many more parameters than are actually present in the feature vector. So we can sort of see here, like, what are the essential steps for every loop of this. Now, like the problem is we're operating on single examples, right? So if you're trying to think about like at what point would it actually be useful to try to accelerate this with GPUs? Well, with this particular algorithm, it's going to be tough because normally, like with GPUs, we want to bundle a lot of data together and operate on very large quantities of elements, very large arrays. And our only hope for this working, because right, we're not going to be able to operate on like thousands of examples at a time, is that the actual function itself for like a single forward or backwards pass is so big. We have um so many parameters that it actually is still beneficial to do this on the GPU. Now, can look a little bit at some more details of how this is implemented. So here's an example of this like actual code. This is in the Julia language. If anyone's curious, there's some links in the meeting description about this as well. But we have this part where we update the value gradient, and right, this is operating, you see, on the feature vector here. So there's a step where we have to do the feature vector update. Then we do this, and then right, this is actually the forward pass where then we get the action values themselves. Right, this is like this part of it. We actually have to compute these things. But we also, by the way, need these action values to follow the epsilon greedy policy, right? Because we need to actually look up all the action values and derive that policy. So we have a few, instances here, and then there's this gradient update step where we do this element-wise addition. So the best way to do this would be like we want to minimize as much as possible data transfer, right? Like between the CPU and GPU. Like ideally, we would have everything on the GPU, and everything would just operate completely on the GPU. But at least the way I've written it here, there are a few steps where that's not going to be possible. So first of all, when we define this feature vector update, right? This is where like we have this mapping from the state to the feature vector. Now, this state and this whole MDP environment we have and how we take steps, like this is most likely, especially if you're writing simple examples, this is going to be something on the CPU. So when we get this transition state, like here's the part where we actually use like the transition function to get the transition state. Like this is all like CPU stuff. So it's clear that at least when we do the feature vector update, that's going to be an instance where we have to transfer, something to the GPU. Like here, most likely what's going to happen is we're going to have a feature vector update defined on like a CPU vector, and then we're just going to have to transfer that to the GPU, even if it's already been allocated. We have to move it. And then there's one other part here, which is a little less obvious because here we need this Q hat. Now, the reason why we need the Q hat, go back to this pseudocode, is or we have to be able to compute this difference or here, these differences for the target value. And even if we have left everything on the GPU, all the parameters, um, all the gradients, those are all living on the GPU. But we do then need to get this one scalar value and use it for the element-wise addition. Um, Now, this could all still exist. I mean, on the GPU as well, I guess. Like, we don't necessarily have to transfer it out, but these are just single values here, right? Like, this is like one number. These are like three individual numbers that are being added. Like, no one would, there's no reason to compute this on the GPU. This is a trivial operation on the CPU, but we will have to extract these two other values here to use. And unfortunately, right, there's going to be some overhead associated with that. And there's no real way around it. The only way around it would be if the entire environment itself was also contained on the GPU, and you could even do the state transition on the GPU. There are some, of course, cases where that might be true, but it's going to be pretty restrictive. And even if that is true, we still have the overhead of this step. Like, even if you did this completely on the GPU, we have this overhead. And the overhead comes from this we have to launch a kernel on the GPU to compute this. And even though I'm not actually using this package currently in the code I have, there is this pretty nice package in Julia. There's been a lot of work put into it. The CUDA package. It actually, I think, handles a lot more stuff than just CUDA itself. So here's an example of I just like, I just installed it on here without really any preparation. It even handles the whole like getting the CUDA toolkit and checking compatibility. So here's like the version info. So we have it installed all this, like this runtime version, and then it shows you what devices you have available, right? So here I'm like setting to this device. So, as an example, like the interface is pretty easy to use. So like if I define this vector, right? This is just like a 64 element vector here, and then I can just copy it to the GPU with this operation. So now you can see these are two different, like this is living in CPU memory, and this is now in GPU memory, right? But it's the same type of array. So now we can look at, how long it takes to do certain things. Like here's an example of copying just all the elements. Like let's say that we then updated this array somehow, like if we're doing a feature vector update. And then we want to then transfer this to the GPU. So this is showing the transfer in both directions. It should actually be pretty similar. For some reason, it's a little different going one way versus the other. So note that this sync call here, this is just to make sure that we actually wait for the operation to finish. So if you just launch something on the GPU, it doesn't block anything. So you could continue to do other tasks. But as soon as you request this piece of data, then you'll actually have to wait for it to finish. Maybe you can structure your algorithm so you can do a few other things in the meantime. Like that would be pretty efficient. And then maybe you'll save some of this overhead. But that's not always possible. Generally, like when we do this feature vector update, like we're going to need to use it immediately. Like that's the whole point. So we might not be able to save on this. So you can see here, this is taking about 200 microseconds, right, to do this transfer, like every time. And this overhead, this like 200 microsecond overhead, this is about the overhead for really doing almost any operation. So even if we just needed to like add two numbers together, it would take this long. Now we get really good scaling when we do this for the same operation over lots of elements. But, there are times when we may have to do it for something where, this would take maybe like a few nanoseconds on the CPU, like this kind of copy operation. And now, it's taking many, many times longer on the GPU. Now I made this graph here. Of course, this depends on my device. So it will depend, but this is showing the transfer time per element when we test this with different size arrays. So we can see here, this is this like about 200 microsecond time for just transferring, one element. It's going to be the same. And then we start getting scaling here where like every time we add, we're just making better use of this overhead where it's not eating into our time. And even out, so this is equivalent to like if you had a 1024 by 1024 matrix and that was like, a set of parameters that you were transferring. That's how many elements this is for this final value here. And we can see that we're still getting scaling, right? So we're still not even like we're still being punished by the overhead, even out at this point of this many elements. I can tell you that like most of the time, like the feature vector itself that you would use in this case, it is not, it's very unlikely to be anywhere close to this big. So at least one of these steps is going to just incur, we're going to be up here at like pretty high overhead, like a lot of wasted time. But it still might be worth it because, right, this is just for data transfer. And this hopefully we only have to do like um couple of times, per iteration loop. The other thing we can test is like a more straight like a more common thing you would expect to do on the GPU, which is doing this element-wise addition. So here, like this test function here, where we just update an array by doing an element-wise sum. This is exactly what you need to do when you do the gradient update, right? That's like this step here, where we do the gradient update. This is going to ultimately be some kind of element-wise addition over one or more arrays. So we can test that on both. And again, do I have a well, anyway, here's the graph of showing how this is scaling for more and more elements. So I terminated this at the point where at this crossover point. Of course, this will continue to scale. So the point here is that on the CPU, like right, this is only taking like point, 6 microseconds per element when we do it for a very small number of elements. Whereas on the GPU, we're up to this at 200 microsecond time, which is the same time we had for the transfer. And on the CPU, once we get to about 65,000 elements, we stop getting any scaling, and we're just gonna flatten out here. Where now we're actually at like how long is this actually taking on the CPU for to add up a single element once we've removed all the overhead. And on the GPU, we're not even close to this being saturated. Like we could go up, 10, like 100 times more elements than this, and we would still continue to get scaling. So it does give you an idea of about like if you reconstructed this graph, let's say on your own device, which you could, do with just the same bit of code, then you could see this crossover point. I mean, it's probably going to be similar regardless of whatever device you have, just because this overhead time is going to be very similar across every device. So, we have some idea of about like how many elements we need. Now, this would relate more to like the size of the network you're using, like how many parameters. So, for example, if we had like a hidden layer of size 1024, then and like several of those stacked together, then that would sort of be the point where even with all the overhead and all the other problems, we have a chance of the operations we're doing that we need to do with those arrays would actually be worth it to transfer to the GPU. But, of course, this is just like a toy example. To actually test this, you would have to have your full implementation of your whole, learning algorithm, and then just have the ability to run it on both the CPU and the GPU and see where that crossover point is. But this is at least showing it for just this one element-wise addition operation. Are there any questions about this?
Yes. So I wonder what are the assumptions under which we are operating. So can't we have a batch of environments running in parallel, and then we are performing the whole update for a batch of environments? Like we are generating action for each individual environment in parallel, and then we are reducing the overhead. I mean, we are not reducing, but we are
Well,
spreading it over more.
sure. I mean, that I don't know how that would help because, like, even if you add more environments in parallel, like every time you get a new state, like let's say you have to transfer that state vector to the GPU. You mean like if you wait for them all and then transfer them all at the same time? Yes, you could do
Yeah,
that.
so essentially, if we are
Yeah,
able to
of
run
course.
a
Yeah,
batch of environments, then
yeah.
we are transferring all the states. And
Hmm.
actually, we want to have two batches to interleave because
Yep.
we can do the computation during the transfer. Like for one batch, we can do the computation. For another batch, we can do the transfer. And these two things
Yes.
can happen in parallel.
Yeah. I mean, in that case, this loop would have to be synced. Um, like between all the different environments. So yeah, you could do that. Yeah, if you want to train in parallel, you could design like a sort of a parallel thing like this where you were updating, a bunch of functions simultaneously. Like you had, yeah, like you could just stack a bunch of these things together.
So the weights are shared. Just each time I generate a vector of actions, I have a
Oh, the
vector of
weights are being, yeah. Okay.
like I'm training a single neural network, but
You mean where the weights are? Yes. Yeah. So now, of course, like the way this algorithm is written, right? This is going one step at a time. Now, there are lots of different ways you could try to do batches with this, including doing Monte Carlo training, where you run an entire like episode. Let's say you get like 1,000 or 10,000 steps, and then you could take all of those states, and transfer them at the same time and do this entire thing. Now, at that point, um, it does change the algorithm. So now in this algorithm, right, we're getting both a new policy and a new value function on every step. And it does affect the convergence properties and the efficiency of the sampling. So you can turn this into a more of a batch gradient update. Um, but now you're starting to mix gradients, right, with different value functions, and you're getting a lot of steps with the same value function. So it can work. You can be more computationally efficient, but you may be less sample efficient. So there's a trade-off there because, like, in this case, you are potentially improving the policy on every individual step, right? Rather than waiting for a big batch. So it would depend on whether that computational, efficiency you got was counterbalanced by, your samples being worse. Like the actual, but yeah, like if you look at actually they don't even have it in the book, but like you can define a Monte Carlo gradient like version of this where you finish an episode, you get all the data, and then you process all the data at once. And even then, typically the way you would do it is you would do again like every individual gradient update separately. That's way less computationally efficient than just turning that into a whole batch, right? And averaging all of those gradients together and then adding it up in one step, right? It's like the difference between doing some batch stochastic gradient descent and stochastic gradient descent with one example at a time. Um, you know, if depending on your problem, you don't really know which approach is going to work best. If the batch size gets too big, you start getting way less efficient gradient updates. But usually you wouldn't want to use a batch size of one either. Um, in this algorithm, like we do, like the most natural way to run it is a batch size of one, which is clearly very computationally inefficient. But yeah, there could be other advantages. Again, if your neural network gets large enough, this still becomes advantageous even with a batch size of one, which I'll show an example in a second, at least for the mountain car problem. But yeah, I mean, this can get pretty complicated with how you interleave things and yeah, form batches. But does that make sense here? How like this right, this action selection, right, is actually going to change on every step because we're going to be using an updated policy function like every step of this, which is one of the advantage of the Sarsa versus a Monte Carlo algorithm where we have to wait until the end to do that. So if you start batching things too much, you might lose some of the advantage of the immediate update that you get with this. But yeah, you could certainly have, 10 or 100 or 1,000 parallel samples going on with this. Yeah, all with the same value. So I mean, you're basically talking about having a case where you have like thousands of parallel trajectories that are all going on with the same value function. And
Yeah,
then
that's
you
one
could
option to
send,
utilize
yeah,
GPU and make GPU computation
yeah,
faster than
sure. Now, of
CPU.
course, remember in that case, right? Each step of this loop will not be any faster, right? It'll be slower. At the very least, it'll be the same or slower, because like let's say it's the same. Like we're doing such a good job with our parallelization that we're now doing 1,000 parallel trajectories at the same rate as it takes to do one. And then we're like averaging them all together. So yeah, you could test that and see if it did give you an improvement in performance. So it certainly wouldn't be any faster per step. The question is whether it converges faster because we have all those parallel things going on. And I don't know. You'd have to test it on a particular problem. But yeah, that maybe is a good idea of something to test. And just saving all those. But yeah, no, I do see what you're saying. This algorithm would basically look the same. It's just that each one of these updates would have like, n of these s's and n s primes, that would all be operating on in parallel. But yeah, it's a question of, yeah, I mean, that would be an advantage if then this whole thing converged in fewer total steps. But you'd have to test it to see if that actually worked. Okay, well, anyway, let's go back to this, let's see, this mountain car problem that we had before. So actually, first of all, let me show some of the results we had from last time. So this is for the value function methods, right? This is where we learn the value function, we try to do policy improvement. I had shown there's sort of three different linear approximation, or two different linear approximation cases that we worked on. The first one was just having this very simple feature vector where like the mountain car state is just, sorry, this is I went over this last time, but the actual problem is there's basically like this valley, there's a car in the valley, and it has to drive back and forth, and it can't just drive up one hill because it doesn't have enough power. So the only way out is to switch direction, build up momentum. That's a setup of the problem. And the state is just the position and velocity of the car is what makes up the state information. So you can construct a very simple normalized feature vector by just, mapping these from -1 to 1. And that was one example of a feature vector we could make. The other example was this tile coding feature vector where we segment the state space into different overlapping tiles. And then as we move the state around, we sort of shift which features are active in this state space. And this is a way to generate a lot more sort of linear parameters to work with by, coarsely segmenting the state space. So these were the options. And then we had showed, so if we try to use just the simple feature vector doing this, these are, there was this parameter study where we saw if we do this with episodic training here, this is another version of the algorithm. You can see there is some cases here where we do get what looks like pretty decent performance, like this just means that the car was able to exit the valley in about 200 or so steps. But it's very inconsistent if we train this. We can see here, at least what we're getting is not really working that successfully. Wait, okay. So here's an example of something that does finish in like less than 200 steps, at least on this trajectory. Now, here's the value function, here's the derived policy function, and this does happen to work on this problem. But you can see this is a very inconsistent result. If I run this a few more times, like the number of times it actually works well is pretty limited. We can see it's sort of trying to learn a similar shaped thing. And then if we go up to the tile coding example, we get much better results because in this case, like we have a lot more information about the state from tile coding. And this is an example of training on the episodic problem. We can see that after, in the first 20% of training, we've already learned a pretty successful policy where this is finishing in about 100 or so steps. And so remember, like in this case, for these algorithms, the policy function is always derived from the value function. Right. So what we're actually learning here is this value function. And the derived policy function is going to look similar to the value function because we end up ultimately wanting to take steps in the state space that lead to higher and higher values. It ends up forming this sort of spiral shape in the state space. And then this trajectory plot is showing the trajectory in the state space, where this is position and velocity on the y-axis. And this is showing just over time the position of the car, where it has to change direction a couple times before exiting. So we have that. So then we had moved on. Are there any questions about this?
Schedule a call Lamborghini with Tesla.
Sorry. Okay. I don't know what that person was saying, but I doubt it was a question about this. Okay. So yeah, then we moved on from tile coding to, oh yeah. So actually, I also made this other plot here, which is showing as we change the complexity of the tile coding, right? So when we do tile coding, we have sort of two things we can control, which is the number of tiles, which is, you can see on this leftmost bar what the number of tiles is doing. It's just creating finer and finer segmentations of the state space. And then the number of tilings is adding like how much overlap there is between these segmentations. When we have, so we're able to layer multiple segmentations together with some offset. And you can see the way this is shaped, like when we do one tiling, this is the same as state aggregation, where we are just segmenting the state space into these buckets. And there's just, the only information we have is like which bucket are we in the state space. When we start adding more tilings, we get more overlap. And now you can see here, like this is a point where two of the tilings overlap, and this is a point where we're just on the edge of this one tiling. And you can see, which is because this is a linear method, the gradient updates and the convergence properties are pretty good. So we get pretty consistent performance here, where when we add tilings and when we add like how many tiles we have, we tend to get a pretty straightforward improvement in the results. This is showing like the average length of time it takes to finish an episode with this learned value function. So you can also see like how the tile coding is working, how it sort of is able to make smoother and smoother looking value functions. And the best results were, here with like the most, it's like the most complex approximation function, where this is like now showing 32 tiles in each direction and also 32 overlapping tilings here. And we get this smooth value function. What's shown down here is the policy function, which is actually, we're not learning directly in this case, but this is the policy function that is actually the greedy policy with respect to the value function, which normally, if policy improvement is working, this is the method we're using to actually, find the optimal policy in this case, or, as close as we can get to it. And here we can see, the best results down here and the general shape of this. We can compare this like policy function, right, with the one we had. Well, it didn't even work actually, but for the simple case, right, clearly, like, you know that when you only have two parameters, you're very limited on the type of function you can form. So like this isn't going to cut it. The one I showed before, I think, was a little bit closer, but we're really only able to draw like a few segmentation lines in this state space. Whereas you can see something closer to what the true policy function is that solves this problem well, and it looks something more like this. Okay, so are there any questions about these different solutions? What we're seeing here? This is an example of a linear method which works pretty well on this problem. And now, if we go to nonlinear methods, we can look at some other parameter studies here. Now, in the nonlinear problem, the results I showed before were using episodic training with a reward of -1 per step. So the value function is going to represent the number of steps to completing an episode. And those values are going to be, in the 100 range or so. Now, with nonlinear approximation, sometimes your approximation function has a lot of trouble dealing with very large values. It tends to work better when all the values are normalized within a tighter range. So it turns out that the continuing version of the problem, right, let's see, these results. Yeah, we can already see somewhat, all these results look bad here just because of the constraint I'm putting on this parameter study. But when we do the continuing problem, we are actually learning the differential value function, which is akin to the values are going to be closer to the average reward. So if we get, let's say, a reward of 1 or 10 or something when we reach the goal of the mountain car problem, which is like exiting, then the function, like the actual, like if it's 1, then the average reward function, those values are all going to be less than 1. They're all going to be, and the differential value function, the values are generally going to be between like -1 and 1, which is pretty helpful, like for the nonlinear approximation to constrain the values like that. So here I'm showing an example of this training. Yeah, doing the nonlinear training, this particular network I'm using, this has the layer size is 64 and there's 8 layers here. And this result is pretty good. Of course, like this takes a lot more training examples to solve. But you can see that the value function that's been learned is much closer to this spiral shape that we're supposed to have. And the performance here, this is now showing the performance in terms of the average reward. So if you take the inverse of this, that would be the number of steps. And you can see that it is, close to that value of 100 or so. However, if you look at the policy function, so like the value function looks somewhat reasonable. Like this looks close to like what we should have. Remember, the policy function is being derived from this. And this looks pretty messy. Like it's not clear exactly how, like despite the fact this is working correctly, this doesn't look that great. And we can see actually in this similar set of plots that I made for the nonlinear approximation, So here we have here, let's just look at this one because this method is a little bit better than the other one. And with the tile coding, I did the training in a very straightforward way. Like this training method is doing a little more complicated manipulation of the learning rate and sort of testing it for a little bit, and then maybe decaying the learning rate. And even despite that, the performance is still pretty inconsistent. You can see all the value functions look similar to each other, except like in these failure cases. But the value functions are a lot less consistent. We're starting to see something that looks a little bit better, where we have these boundaries. I mean, clearly there's a pattern here where this is showing the policy distribution for the acceleration action. So red is 1 and blue is 0. So red means that this action would be taken in this part of the state space. And we can see this general shape, but like even here where this is a successful policy, but this shape and where these gaps are is quite different from this policy function up here. And then in these failure cases, we see something which is almost working, but there are these really sharp, sort of chaotic boundaries where it seems hard to control exactly where this boundary is with these derived policy functions. I mean, nevertheless, this whatever 64. This is also, as we go down to the right, the lower right corner, this is getting more and more complex. So the best results here are for this 64 by 8 network, but we can see actually it's not. I mean, we're not getting that much of an improvement from just this 4 by 8 network either, right? Where this is also finishing in less than 110 steps with here. So we can see like we can certainly solve this problem with nonlinear approximation, even with this very simple. These are just like fully connected networks. It's like the simplest neural network architecture that you could use. But I said we would look at some of the performance here and when it might make sense to use a GPU. So we saw we could already solve this problem with a pretty small network. So clearly, like you can probably already guess that for the size of the network I showed, it would not be advantageous to use the GPU for that. Right? But we can still see, even though we don't need it, we can see like what would we actually need in order to accomplish, like what size of network would be necessary for it to make sense to use the GPU. So here I'm just showing some profiling of this entire training function here with nonlinear approximation. We can see roughly like how much time is being spent on different steps. So this is showing what is like certainly a larger network than we need, but still pretty small by the standards of how large neural networks can get. And we can see where most of the time is being spent because of, again, how small this network is. There's like this is the sample action part of the algorithm where we just use like we've already computed the action values and we're just sampling a new action. We can see this, all these other steps are so fast. This is actually a significant chunk of the time. This is the parameter update part of the algorithm. This is something about eligibility traces, which is something we didn't talk about, but you don't have to worry about it. It just adds a few extra steps to the algorithm. And then the gradient update is over here. Right? So this normally we would expect to be the biggest chunk of time. You can see it is the single biggest chunk of time. And we have, the time is sort of equally split between some copy operations, and then this is the matrix multiplication function that takes place in the gradient update. Which is just a blast function. Now we can compare this to what the profile looks like if we have a much larger network. So this is like 512 by 2 instead of 64. And we can see now, now we can actually see the forward pass showing up here. So here's, right, like the forward pass you can't even see here because it's such a small amount of time. The gradient update now is taking up more than half of the total time here. So again, most of the time being spent on matrix multiplication and copying. And then we have the parameter update taking up, a little bit more time, but about the same. And now, okay, so now if we compare this, now here's an example of running this where I've set this GPU flag to true. So now it's doing this computation on the GPU. And you can see here, this is for 10,000 steps. Oh, sorry, this was 10,000 steps and 245 milliseconds for this. Now, this is way too small for the point where we'd expect the GPU to help. You can see here, like this is now 2 seconds for only 1,000 steps here. So clearly much, much slower. And we can see where a lot of the time is being spent. So we have this mem copy, right? This is the part where we have to copy the feature vector. And then in this forward pass, when we update the action values, we have another mem copy where we have to then extract the output value from the forward pass. And then we can see the actual like value gradient update that operates on the GPU is not taking up very much time, right, over here. If we do this here, I run this for a significantly larger network, right? This is 4096 now hidden layer size. And we can see actually the total time is not very much longer. And that is because these things scale very well on the GPU. And we can see here, actually this mem copy operation now is taking up a huge chunk of time. However, now notice this profiler, this is not a GPU profiler. This is from the perspective of the CPU. Now, this mem copy operation, I believe what's happening here is actually these operations, like these, so this is the gradient update, here. Now, this part of it is the part that actually like does the backward pass and does the matrix multiplication. This is the mem copy. However, the way the profiler is working is it's just looking at how long these are taking on the CPU. When we make this call to CUDA mem copy, what's actually happening is it's waiting for this result to finish for the copy. So this big extension in time here that we're seeing is actually just the matrix multiplication stuff taking longer on the GPU. This part of it is just the actual copy of the feature vector. So like this section you see here is actually how long it takes to do that mem copy. This big chunk here is probably mostly waiting for this operation to finish. You can see that it's actually taking longer than here. And at no point in this update loop am I actually copying the parameters themselves. So the parameters and the gradients, they're staying on the GPU the whole time. This mem copy is only being used to copy the feature vector or the action value output. So very little. So this shouldn't actually be taking longer, but this is reflecting this step taking longer. Same thing here. Here you could see the forward pass here is this small chunk of time. The mem copy is big, but this is just waiting for this to finish. Because when we operate on something this big, like most of the time in this case is actually being spent computing the matrix multiplications on the GPU. And here's some benchmarking results. So what's being shown here is like at what point do we get a significant speed up? So here, you can think of this as just like per step. I just did this for 100 steps, so this benchmark would finish quickly enough. But here we have a layer size of 2048 and 2 layers. And we can see that using the GPU, this took 177 milliseconds. And on the CPU, it took 1.6 seconds. So clearly this is a point where even using single examples, right, and without bundling anything or trying to do things in big batches, we still get a significant speed up. And we can sort of start scaling it down and see at what point this is no longer true. So here, this is just 1024. That's sort of the break-even point I mentioned before with the element-wise addition. And we can see here, it's still about twice, 2 to 3 times faster on the GPU, at least, with this algorithm. And then as we start getting this, I now have the layer size again. So this is 512, but 8 layers of it. And this actually still also has a GPU advantage, right? It's still, 300 milliseconds versus 500 or so. And it's only when we really get down to this small of a layer size where we no longer have an advantage. This is even going out to 128 layers of this, 256. And now this is now at the point where with this, single example batch size, this is no longer working. We'd be better off just leaving it on the CPU. And these are all, these were all for Sarsa. I believe I have the same benchmarks for the other algorithm, but the results should be very similar. Yeah, it's almost the same where we get. Actually, this algorithm, what I think it was Victor mentioned about bundling or stacking things together, and using that on the GPU. This algorithm, which is different from the Sarsa one, actually has a step where it computes the action values for a collection of transition states. If you have the right kind of environment, you can actually bundle these together. And this is a case where if this part of the algorithm where we calculate the action values, if there's a lot of action values especially, this will take advantage of all that bundling, because this will actually populate a matrix of all of the feature vectors of the transition states, and then it'll compute all of those in a single batch and get all the values out in a single batch. So in this problem, there's only 3 action values for the mountaincar problem, so it doesn't have much of an advantage. But if you had an environment with a lot more actions, like 100 actions or something, you would start getting a lot more scaling with this step. We can see here with only 3 actions, this ends up operating about the same break-even points, right? Where we still get a significant speed up with 1024, but then as we drop down here, now it's eroding away, and by the time we get to 256, now the GPU is gonna not be a factor anymore. So any questions about this performance scaling? If you get like all this code to do the GPU version of the algorithm, you can get through the GitHub link. It should all be in the same repository. I guess I can let me actually show just one piece of this but when we do want to use the GPU, and the GPU is available, when we do the value function methods, this step here, this instantiates all of these things that are necessary for the backwards pass that are just going to stay on the GPU the whole time. Where we have the parameters, the gradient, and some other objects, and then all these update functions, if they can operate only on the GPU. Here is the part where we have to do this mem copy, where we have to transfer the feature vector, and then again when we get the action values, we have to do the same kind of thing where we get the action values back off the GPU. And again, foregoing this transfer wouldn't even help that much, because we would still have to call some other operation on the GPU that would have the same kind of overhead as this copy operation does. And then, when we actually have this flag where we use the GPU, then we construct this GPU feature update, which is we just have to define the feature vector update on the CPU, and then this will just create the same vector on the GPU, do the transfer, and then we have to just use the GPU version of the parameters and the gradient and the update thing. Yeah, so I set this up so it is, once you have the problem set up, it is very easy to just test it on both and see where it's better. Okay, so for the remainder of the time, now I want to move on to the policy gradient approach, which is quite a bit different. And of course, it's the last thing we covered in the book. So with policy gradient methods, we attempt to directly learn a policy function with parameters. And this policy function will then calculate, when we give it a state, the probability of taking every action. So it'll produce a probability distribution. It'll be a naturally stochastic policy. And the policy gradient theorem is something that allows us to compute a gradient which will optimize the policy function with respect to this performance metric. Now, in the episodic case, the performance metric is the value from the starting state where we start an episode, or a distribution over starting states in an episode. In the continuing case, which is probably a little easier to understand, the performance metric is the average reward, which is denoted this R pi. So this is the average reward per step for a policy pi. And it probably makes a lot of intuitive sense that our goal when we have this approximation set up is to maximize the average reward per step. And with the policy gradient theorem, we have a way of actually computing this gradient, which is this right here. And this is an expected value, which means that everything inside the expected value, we can actually replace with a sample, an unbiased sample. And we see here, this is the true value function. And sorry, this is the original formulation of this. We also derived in the book, you can actually rewrite this in a different way. So we ended up rewriting this gradient update. This is the method with, oh no, you know what? Actually, I've already written this out actually in the way that we practically use. So we need some sample of this. And if we use a Monte Carlo method, we could just sample this directly once we complete a trajectory. But oftentimes we again use the bootstrapping trick for this, where we actually use a value function that we're simultaneously learning at the same time as the policy function. And we use that as an estimate. And that does again break this assumption that this is an unbiased estimate of the state action value. If we're using a bootstrap estimate, it probably won't be, especially because it's going to be converging to this TD fixed point. It has approximation errors, etc. But often we can sweep all that under the rug and try to see if it works. If we're really worried about that, this much simpler reinforce algorithm, which is the first one we introduced in the book, this one actually does use this sample here, G, where this is an unbiased sample of Q, SA, and this doesn't break any of those assumptions. But this only works if we have an episodic environment and if we wait until an episode is terminated before collecting, before doing any gradient update. So I have this, yeah, okay. So in the Monte Carlo method, we use G. In the actor critic methods, we have to also train this V hat, and we actually train V hat in the same way we did up here. However, we're not deriving the policy from V hat in this case. We are only using it as a way to compute this gradient, this target value for the gradient. So I have this little comparison table between the methods. It might be a little, I don't know, hopefully it's still readable, even though it's kind of smaller than I want it to be. But Does this look okay to people?
Yeah,
This
it looks
visible?
fine to me.
Okay, so I just kind of went, these are just a few of the main highlight points comparing the two methods. So for both, we need this feature vector mapping. We also need a target value, right, which is something we're using to get this expected value. And we already covered how it could either be a Monte Carlo sample or a bootstrap estimate. But that constraint is going to be the same for both. Now, the value function in policy gradient methods, it is optional. We do need the state value function approximation if we do actor critic methods. But we also might not need it if we use the reinforce algorithm. Whereas when we do value function approximation, it's the whole thing we need. We either need to compute Q hat or V hat. The policy function and policy gradient is an explicit function with its own set of parameters, theta, right? It's a function which will tell us the probability of the action given the state or the feature vector assigned to a state. And in the case of the value methods, we always derive the policy. And what we derive as a deterministic policy, we do have to use epsilon. We have to make it epsilon greedy sort of artificially in order to guarantee that we explore the state space. And that's another parameter that we have to use, right? We have to select which value of epsilon we're using, which controls how often we take random actions. Then in both cases, we do need a gradient. For the value methods, we already, we need just the gradient of the value function itself. In these methods, we need to compute, right, this gradient. So this can also be rewritten as the gradient of the natural log of the policy function. But we need some way of computing this. And the value gradient is optional depending on if we are using that as a bootstrap target to get the sample, the return sample. And then for value methods, well, okay, I already covered that. Yeah, we need the value gradient. Now, the policy gradient method has a big theoretical advantage, which is that with a policy gradient theorem, we should actually be able to change the parameters in order to maximize the performance metric that we care about. Especially if we use a linear method, we shouldn't have any local optima to worry about. So we do have a way, some theoretical guarantee of reaching this optimal policy with respect to the parameters that we're using. Whereas with the value function approximation, we're using the greedy policy and we're hoping that the policy improvement theorem will apply, that our approximation isn't so bad that it will, it will fail, which it certainly could fail. We saw in the really simple case of the mountaincar example where we do get some weird behavior. If the value function is too simple, especially in the simple linear case where we just have two parameters, where we get pretty unstable performance. Also, because of the policy gradient theorem, the thing that we're optimizing here is actually accounting for how the policy function is limited. So like based on how the feature vector mapping takes place and how many parameters we have, our policy function can only do certain things. Like it's not arbitrarily complicated. So ideally what we want is the best we can do with that constraint, which is what the policy gradient will give us. In the value approach, our policy function or our value function could actually sabotage us. Like if it's too simple, it might not work to begin with. So we are, minimizing the value error, which is accounting for the constraints on our function. But, that function that minimizes the value error, again, is not necessarily going to be something for which improvement works on. And then with the value approaches, we do have to set epsilon because we have this epsilon greedy action selection. In the policy gradient methods, we really just rely on the policy itself to explore the environment. And the policy will begin very stochastic, over time it can become more deterministic, but we really care about the states that we visit close to the optimal policy. So it will end up naturally concentrating our samples on the states that we actually care about and that are important for the approximation. And as long as our learning rate isn't too high, we won't get to a case where, we reach a deterministic policy too quickly and we fail to explore. I mean, but with any gradient method, right, you can always fail by having a learning rate which is too high. So that's always something that you have to be worried about. So I already mentioned how, we should have maybe some advantage from the policy gradient approach. Are there any questions about this comparison? I know this is like a very broad overview. If you want all the mathematical details, you have to go back and look at all the previous meetings.
Could you explain the idea of bias, especially when it comes to the G that you showed in the reinforce algorithm?
So in the reinforced algorithm, well, so for all these algorithms, like we need to use, we need like a sample of this, right?
Yeah.
Which is the action value. When we use G, that is just an unbiased sample of this. But if we do like an actor critic method, like shown here, then wait, is this showing the one step? Yeah. So now with this method, we don't have access to G because we're doing this step by step. We haven't like completed an episode yet.
Right.
So we have to replace it with this, which is what we did like in the value methods, where this is now like our stand-in for G. But notice like this is using this approximation function. Now, this approximation function, especially prior to us like training the parameters, could be anything. The value could be completely wrong. Now, like in a tabular setting, this would just be like an average of the returns we get at this particular state. And over time, it would become an unbiased sample of this. But because we're doing approximation and we have this value error objective, like this is what we're using to approximate the value function. Here, like we're minimizing this. Like this whole process of computing this value function, especially since now we are also using a semi-gradient method to update the value function, probably if we're in that actor critic setting, we no longer have any guarantee that this V hat is going to be, in fact, like we know it's going to be wrong because we know it's going to converge to the TD fixed point. Like it's not even gonna minimize the value error.
Gotcha, because you're doing the TD.
But even if
yeah.
But even if we don't, like even if we're minimizing the value error, still this is not going to be like an unbiased sample, right?
I see.
I mean, you can go back to this, like here's this here. So here we have the Monte Carlo estimate. Like the whole point of this chart is to show that these values out here, the reason why our error is worse for these states than for these states is because these states aren't visited as much.
Gotcha.
And the value error actually depends on the state, like the distribution of state visits. So we're prioritizing lower error for more frequently visited states, which is, there are good reasons to do that. But it also means that now when we sample this value here, like this is no longer an unbiased, like there's clearly a bias to this value. And there's even more bias when we use the TD estimate.
Gotcha. I see.
But,
so is there something here to say that that's the reason you would use a batch to update
no, I mean,
using the gradients, or you're trying to be somewhere in between the two, like instead of doing a single step or updating with just a single state as opposed to waiting for the entire episode to finish, or something like that. Use like a trajectory, which is what.
Sure. Well, the batch versus not batch isn't really the same as this problem.
Oh, sure, because the batch could just be like,
I mean, a batch will still be in that context a collection of transitions, but still
right,
of single step transitions.
right. And
If you
the
really,
starting states don't have to be the same for each of the steps in the batch, is what you mean, right?
you probably wouldn't want them to be because you want a variety. Like if you're just repeating the same
Mm,
trajectory, it's not a useful batch.
right, right.
You'd want, but again, like you have other batch problems where now you're averaging gradient updates together from different parts of the state space, and who knows, like typically, I'm saying you can get worse problems doing that than the problems you get when you do supervised learning and your batch size is too big and you get really inefficient learning. Like there's a lot more worse things that can happen with these algorithms because you don't have a fixed data set. Like you're also manipulating the data itself by these gradient updates. Like
Right.
it impacts the future data you're collecting as well. But the pure reinforced algorithm, which is a without a baseline, which is also not great, is free from any of these problems because we always have this sample and we do wait for the trajectory to finish. Actually,
Right.
even with baseline, because it's a Monte Carlo method, this baseline, practically, we do use a value function to compute the baseline. It actually could be a constant. And this value, whatever this value is, doesn't affect the convergence of this at all. Because the only thing, this can't depend on the action, this baseline value. That's the
Right.
only
Yeah.
constraint on it. As long as this doesn't depend on the action, this will not mess up our gradient at all. Because we
Mm.
have the advantage. We're starting with G, which we already know is an unbiased estimate. Now, once we get into the actor critic method, now we no longer have anything which is an unbiased sample of G. So we're on a little bit shakier ground.
Right. And because you're doing even one step of approximations, that's also gonna
Yeah.
affect
Well,
it.
now you can fix some of this when you start adding eligibility traces. You can start approaching the performance of Monte Carlo methods without needing to actually wait. And that's where, if you go back to the videos where we discussed eligibility traces, there's a lot more detail on that. But some of these methods will tend to perform better when you set, I mean, we can actually get into the actual results here, but when we set lambda, I show it here. Yeah, so if you look at these parameter studies, actually, here's like, wait, the tile coding parameter studies, you can see here that the best performing things, right? This is lambda is 0.99. That means that we're using eligibility traces in such a way that we're approaching like Monte Carlo sampling.
Gotcha.
We're sort of simulating Monte Carlo sampling without actually doing it. The point is, by the time we're done with the training process, hopefully the gradient that we've accumulated will be similar to what if we had actually waited until the end. But we have the advantage of updating it along the way as well. And at least for this problem, even though we have these problems of bootstrapping, some of those can be corrected a bit by having accumulating gradients for a longer period of time. So like these high values of lambda and end up sort of doing a decaying like average of the gradient over many steps as we progress forwards, which ends up having the effect of like if we had averaged a bunch of future steps for our original update.
Gotcha.
But we end up doing it in an efficient way in real time. And again, it's too much to get into here, but yeah, there's an entire sort of chapter covering eligibility traces.
Gotcha.
But for now, yeah, so I talked about, so the policy gradient method, they have some advantages. Like the main advantage is that we're actually optimizing something like directly with the gradient. We're optimizing the performance rather than just hoping that we have good performance. So we can now sort of repeat all the same learning like with the same feature vectors we had before, but looking at policy gradient. And I'm just going to skip to the actor critic method. Like there's no point in looking at all the different variations. We have this actor critic eligibility trace algorithm, which sort of subsumes all the methods. We can sort of approach the performance of reinforce if we set lambda values really high. So here is a parameter. So now here the parameter study, I'm just showing it as a table because we have a lot more parameters to worry about. Right? We have now 2 learning rates. Right? We have the learning rate for the policy parameters and the value parameters. And then we have these are the eligibility trace parameter, which, if these are set at 0, that is just equivalent to the like SARSA method or the one-step TD learning we had before. And remember, so this is the simple linear results. This is where we just take the state, the 2 like numbers in the state, and use that as a linear feature vector, which sounds like a pretty bad idea because we have very little information now. Like we're just relying on this. But we can see that with the policy gradient method, this is the result after, figuring out what are some good training parameters for it. Here, these are the learning rates. Here, this lambda 0.9, it's pretty high, right, for the state value function approximation. And we can see here now we have what looks like pretty stable performance. Like this is not a chaotic looking policy function. There's clearly a clear delineation between the 3 actions. And also what it's done is, right, this function is extremely limited in what it can do, right? However, like within that limitation, it has found a partition of the action probabilities that actually works. We have the acceleration action in this part of the state space. And then this is probably a part of the state space, which is we avoid or don't visit much because this is the like no op action where we don't do anything. And then this is the accelerating backwards action where you go backwards. We can see, I mean, this performance is actually pretty comparable even to the best I mean, let's say like the best performance we could get is around 100 steps in this problem. And we can see even with this, like the simplest possible function that we could use that does distinguish between the states, we're getting pretty decent performance. And if we could, like, this is extremely different from the result we get with the value function method. Now we can also look at the tile coding again. We have, again, episodic training for linear methods tends to work much better than the continuing training. The linear methods don't have any problem with these large values, like 100 or so. There's no convergence problems. The gradients are fine. These large numerical values only really become a problem with nonlinear approximation. So here's an example of a tile coding solution. This is, again, 16 tiles, 8 tilings. And we can see the same sort of spiral shape we got before with the value function, but now the policy function looks quite a bit different. And again, this is the thing that is being directly learned in this case. Actually, maybe I should compare it to, let's see, tile coding. So again, this was a tile coding result we had. The value function looks a little bit nicer here. Again, it's the thing we're relying on primarily. The policy function, though, looks a little messier, although it is very similar in structure. This performance was a little bit worse as well. And then again, this is the tile coding solution. We can see it does have, though, a pretty different looking policy function. It's, again, similar, but there's no reason why we'd expect these 2 solutions to be the same, because this, again, is trying to directly optimize the performance with the constraints that we've given it, which is, these tiles. And I then made this similar plot where we can see what the different solutions look like as we increase the number of tiles. And another thing we can see here is that even with far fewer tiles, right? So here, this is only 4 tiles in each direction. And, you know, here, like 4 tilings, right? This is a very minimal feature vector. We already get like something close to optimal performance here. 8 tilings, 16. Like, so if we go back to this one, we can see that we had to get quite a lot more complexity in the function before we got really good performance. Right? Like here, like we can see that a necessity for these methods is to have like a pretty good looking value function, which is fairly close to the true one in order to have good performance, right? Because we are like deriving this from the value function. But if we go back to the policy one, we can see that actually it doesn't take much to have a successful policy function. Like here, we really only need this rough shape where we have this little bit of a cutout in this part of the state space. I mean, like we generally have this partition where the upper part of it is acceleration and the lower part is deceleration. And then to really get, you know, good performance, we need to add this little bit of extra complexity where we add this extra little space where we decelerate. And it doesn't take very many tiles to achieve that. And actually, when we add more tilings here, we start getting worse performance because this probably needs more training steps to actually learn this. Like the issue here is that these haven't had time to converge yet to the correct thing, because it's way easier to converge these functions than these ones with lower complexity. You can see here, like the value function also doesn't need to be perfect. Like here, like this is great performance here, like 102, 101 steps. This value function really does not look like the correct value function. It's pretty far away from it. But again, this is not what we're relying on. This is just being used to help with that target value that we're using for the gradient update. But we can see that like this isn't going to do more than it needs to. And even when we get down here, where now these do look closer to the true value function, they're not really matching the value function. Because they don't need to, right? Here, again, like I believe this would probably achieve performance equal or greater than this if we allowed it to train longer. But given the simplicity of this shape for the policy, we're actually better off just using fewer parameters because this is faster to learn. And then again, like the one, you can see in the one tiling case, this is just state aggregation. There is no overlap between states here. So any questions about these solutions, or these are just the linear solutions, but this compared to the simple one. Yeah, this was the really simple linear solution. And then these are the tile ones. The one problem with the actor critic methods is we can see with the value function method, the number of steps I gave it was plenty of time to converge those value functions. Of course, they're not going to do any better than that, probably. This has a much higher ceiling in performance, and as a result, may require a lot more training steps to learn. Like here, like our performance here should not be worse than here, but it is because we haven't given it enough samples yet. Okay, well, we can move on now to the nonlinear results, which again, you'll see there is a big advantage in this case as well with the simple linear method, like the really simple one. It's a big improvement. And the nonlinear methods also have a similar advantage in this case. This is showing the continuing problem parameter study training. Again, like you don't have much success with this with the episodic problem because of those large values that you get in the estimate. So here's a training example the same actor critic method, continuing formulation of the problem. And this is not a very big network either, right? This is a layer size of 32, 8 layers. And this is the result. We can see the learning curve here. This has, I mean, this probably would improve further with more training, but this is looking like a pretty consistent performance improvement as we continue the training. And we can see that the policy function it's learned has a very clear, stable shape. Again, like this action 2 here, this is the no op action. And as this training is continuing, like the highest probability here is like 0.1, 0.12. So this is basically going away completely, but this isn't relying on taking these arg maxes, which we have to do when we derive the value function, right? This is able to smoothly learn a continuous policy function. And this boundary here is allowed to be as sharp or as smooth as it needs to be. Like here, it's learned a pretty sharp boundary, but along the way training this could start it out much more blurry and then over time become more sharply delineated. And the key feature here, like the key difference between like an okay policy, which solves the task in 150 to 200 steps, and one that really can solve it in like 100 or less, is this precise shape of this cutout here in the policy in the state space. And the value function here also looks like pretty close to the true one. Now, one of the reasons why this value function looks pretty good and maybe better than the tile coding one is with the nonlinear version of this actor critic, these networks are actually sharing most of their parameters. So the only difference here is in the output layer. So for the policy function, the output layer is generating 3 different preference values for the 3 actions. And the value function is just taking the same layer prior to that and turning it into a single state value. So that sharing of parameters may actually help both functions stay consistent and have similar performance. It's kind of nice conceptually because ideally, like all of the information we learn about how to get the optimal policy should also be relevant for the value function. And if we compare this to what we had learned in the value method, like here were the policy functions we had before. And the reason why all these delineations are super sharp, jagged, and a little bit unstable, like exactly where these boundaries are, is because we're not really directly learning this boundary. We're deriving it from this, and we're trying to learn a smooth value function. And then these policies are inherently deterministic. Like this method doesn't allow for any stochastic action selection. And the problem is with a lot of environments, depending on how our feature vector is constrained, like it's not able to capture the entire information of the state. And our approximation function is limited, then we may not actually be able to get the correct value function or like to get these boundaries correct. And the best policy may be a stochastic one. It may not have these sharp delineations. And every step along the way of this training process with the value method, we have a deterministic policy that we have derived. Whereas in the policy gradient method, this can smoothly go from something that looks all washed out and fairly random to this. Actually, one thing that might be cool, which I should maybe add, is a visualization of the policy during the training process. Yeah, that I didn't think of doing that for this, but it'd be cool to see how, because right, it has to start from like a random policy and then discover this. And if it's able to do that in a smooth fashion, it's way easier. And we can see there's sort of this transition point where it does very rapidly learn the correct policy function. I have this performance profiling for the actor critic method. The point is, I did again find this point where the GPU method is useful. here, let's see, 512 by 4. This took 5 seconds. So this is about the crossover point for the actor critic method where the GPU becomes useful. Anything more complex than this, 512 by 4 layers, the GPU will start having an advantage. Here's an example of a pretty big advantage, right? This is 1024, 2 layers, and this is 8 seconds on the CPU and only 4 seconds on the GPU. And look, like a third of this time is just on the parameter initialization. So if I let this run for 10,000 or 100,000 steps, this time would go away to 0, and this would have an even a larger advantage than this. But the crossover point is about the same as before. It's about this like 1024 layer sizes where you start getting a real advantage. And then here is this solution study plot of the policy gradient method. And we can see that and this also isn't trained with a lot of like tweaking of the learning rate. This is trained in a very straightforward manner, similar to the tile coding method. And we can see that we get very consistently improving performance as we make the network more complex. Again, down here where we have 64 and like 8 layers, the reason why this isn't as good is probably because it needs more samples. As we can see, even going down to here, 32 by 8, we get this, really good performance, like less than 100 steps average. And we even actually get that good performance with this, right? For like here we have failure cases here because this is a really small number, right? I mean, 4 units per layer. But you can see like the value function is learning is almost the same as even the really complex network. Like the only limitation here is as we get very few neurons, right? We're going to be less able to faithfully reproduce this shape that we need. We can see the best performing shape is we have this pretty flat area and then a pretty rapid rise to make this notch. And if you look at also with the layers, as we start at 2 and then go to 4 and 8, the main thing that changes is that we're better able to represent the sharpness of this shape. Right? Even if we have a lot of units, if we only have 2 layers, we're limited in how sharp we can make this shape. And then, even with only 8 units here, like with 8 layers. And of course, I didn't test this with 16 or 32 layers, but who knows? It's possible that even with like 4 or even 2 units per layer with a much deeper network, you could already get good results if you add enough layers. So, okay, that is the end of all the results. Let's see, I covered policy gradient. I think I covered pretty much everything I wanted to with the performance, when the GPU makes sense, and then the advantage of the policy gradient methods. Are there any questions about any of that? Did I gloss over anything? I was hoping to make it more obvious in the actual results how a lot of these policy gradient advantages become pretty obvious when you look at certain results. Especially this one. Like this is right. It is surprising that this even works given how simple this approximation function is. And we had a previous meeting recording also where we did a big overview of the tabular method. So this, I guess, kind of concludes the other side of that, where now we've done kind of a broad overview of all of the approximation methods. So we will have to decide what to do in the next meeting. If anyone has a comment or idea about what they'd like to see covered, we should go on with more case studies, or maybe combining more techniques together. Like is hinted at here. There are some of these other search methods, and hybrid methods. We could do that too. I know Evelyn also posted another book about cooperative learning or multi-agent learning. That's another option to look at. But does anyone here have any preference or idea for what to cover in future meetings?
Yeah, I was also kind of looking into a couple of like a book or two about like planning or decision making, but yeah.
Planning, yeah. There is some discussion of planning in the book. I guess the meeting we had that covered chapter 8 talked about that a little bit. With planning methods, and I do have some stuff on Monte Carlo tree search we could look at as well. And this is sort of, I mean, another option is to look at some of like the AlphaZero style algorithm. Those have, an interesting combination of techniques, including tree search, policy function, value function, and sort of seeing how to implement it in this package might be kind of interesting. There is also, in part 3 of the book, another section on case studies, and maybe some of these case studies would be interesting to look at as well. But yeah, if anyone's here and didn't like participate in the earlier meetings, even though we have recordings of it, another option is to like do some of the chapter overviews again, especially if there is a chapter that people have looked at or find confusing. We could do another video just covering one of the basic chapters in the book.
Wait, just wanted to check, like all of these notes that you've taken, are these like publicly available on the GitHub or?
Yeah. Mm-hmm.
Okay.
Yeah, so it should be in the meeting description. There's links, but you could check. I mean, yeah, check the meeting description, and you can let me know if it's not obvious or something.
Okay. Sounds
All
good.
of that should be there. Yeah, all these notes are there, and also like even this should be added to like one of the branches. It's not. Yeah, I haven't like put it in the main branch yet because it's still sort of like a work in progress. But yeah, and this is also set up so that like you can import this as a package as well and use it. Like here I'm using it in these notebooks because it's good for presenting, but it's designed like you should be able to import it and use it as a package. Just all the the functions are available. I haven't quite written out all the like documentation of how, but there's some basic instructions of how to at least just install it and get started with it.
I got you. Okay.
Yeah, and like right now it's not using this CUDA package I showed here. It's using something else, which is more basic functionality that just lets you use the CUDA driver, and there's like custom kernels in it to do a lot of the stuff. But it's the same basic idea. Like if I were to use this package, I would also use it with like the most basic functionality anyway. But the advantage of using this package is that you can write kernels here and actually use the Julia compiler to compile them to the PTX code for the GPU. So that's like the big selling point of this package. So like what I did here is something you'd normally never be able to do, which is where here, like I've just written an element-wise addition on GPU objects, and this is automatically compiling the kernel to do this operation. Hopefully in an efficient way, but this type of operation is common enough that like this is a pretty straightforward kernel, so it's easy to automate like this kind of broadcast operation on the GPU. But this package also lets you write your own custom kernels and like CUDA-C, and then it will compile them in real time. And the advantage of that is then when you switch devices, or it will just recompile the code you need. So it's pretty flexible with the setup, like with the initialization and the closing things down as well. But yeah, a
Wait,
lot
could you
of
also
work.
go back to the visualizations of the CUDA code? I think it was the blue timing visualizations. I was just trying to understand like what those were. Like I think it was talking about like different functions and giving them different blocks, right?
These flame graphs.
Yeah.
Yeah, so this is like profiling on the CPU. So it is showing GPU
Yeah.
operations here, but from the perspective of the CPU. Actually, with this package, another advantage of using this package is you can use the GPU profiler as well. So you could see
Okay.
also what's happening on the GPU. So here is a version of the function running without GPU acceleration.
Okay. But like what's the left to right and like top bottom?
Oh, so
like,
top to
what are
bottom is
the
showing depth in the call graph. So like this is
Okay.
the top level function. Is
Makes
like
sense.
Sarsa lambda is the algorithm being run.
Okay.
And then these are the pieces of it.
So
The
it's
horizontal
showing the portion.
representing
Okay.
how much time each step is taking.
Okay.
And yeah, I mean, some of these things are maybe hard to read because like what these things are doing, but you know, like materialize, copy to like these operations are just sort of element-wise operations, especially like this parameter update is doing, you know, this element-wise addition. But the way that works, it's doing it in place. So you have these copy to materialize. That's just representing the fact that these are like we're copying values into the original parameter matrix here. And these, you know, gem v. If you're ever familiar with using blast functions, ultimately, if you're doing matrix multiplication or matrix vector multiplication, you're hopefully dispatching to one of these things.
Okay.
Gem v. This is a matrix vector multiply. This is matrix multiply.
Okay.
Yeah, and these are blanks. And there's
And then does the
corresponding-
coloration like signify anything, or is it just like function
Yeah,
names?
it does. Actually, this is red. So if the color is red, which is kind of bad, I mean it's red. It indicates to you that means you can see here a flags runtime dispatch. This tiny little thing is red because this code doesn't have these problems. But yeah, and yellow is garbage collection. So here you can see this little sliver of yellow. The GPU code kind of inherently will have some runtime dispatch and garbage collection just because of these pointer objects, and we're not really, the function calls or launching kernels and they're doing things that, you know, but the runtime dispatch is sort of irrelevant for the GPU code. The CPU code you can see. So the goal would be, if you have some algorithm you've written here, to not see any yellow or red.
Okay. Yeah.
That would mean you're not wasting any time in garbage collect. I mean, red is really bad because that could mean that your code isn't even getting compiled to something efficient because the compiler can't infer what the right function is or what the types are. So it has to make just a very generic version of something.
Okay.
So that would be a lot of, if you're writing this and sort of optimizing it, a lot of the work would be to, this is very useful to identify problems like that.
Yeah, makes sense.
But you can see these operations are, all of these written here are CPU operations in that they run on the CPU, they might dispatch to something on the GPU.
Okay.
But here, like this, see this is the final thing here, like launch kernel. So this is the thing that's actually sending the job to the GPU. But from here, we can't actually see what's happening on the GPU. We can only see the time. The only hint here, like I said, is this mem copy, how long this is. The hint is that this is waiting. It's waiting for this to finish. So really most of this time is what we want, which is the computation time of the gradient update.
Okay. Wait, how do you know that it's waiting though?
I don't, but this mem copy needs to sync the GPU. So This will
Mm.
automatically call a sync operation, whereas this entire like backwards pass gradient calculation is happening on the GPU. Like all the memory objects are on the GPU. So all the CPU has to do is send this instruction to the GPU to do this, and then
Okay.
all of that will run, and then it won't block at all. Like
Mm.
wait, it'll only block when I actually ask for the value, which is happening here.
Yeah.
But because I can't actually see the GPU profiler, I'm not seeing the true time for this. But yeah, I haven't. I'm unable to use the GPU profiler like in this notebook for this code like this. But you can get an idea of what's happening here. And again, like the only mem copy happening here it's a very small amount of data. So the mem copy itself will only take the overhead time, basically, which is that about 200 microseconds per transfer, which starts to become irrelevant when you have really long time being spent on matrix multiplications. But that's why if you have a really small network, that overhead time really kills you when you're doing the transfer.
Yep. Okay.
And that overhead is true even when you launch any of these things. Even if you perform an operation purely on the GPU, like you're still going to have that same overhead time of launching the kernel.